stop. Okay, maybe next time we do the other things. Huh? But if you have any things that you want to ask, you can ask also. Right? Then I can start this theorem, whichever
Okay.
way. Is there anything that you would like to know in general? Okay, we'll have conversation anyway, anytime. Huh?
Sure.
All right, then I will go with my lecture. Actually, these are all very nice. Original cinema was wonderful. Huh? We showed it in a normal uh, topological space. If I take two disjoint closed sets A and B, I can find a function f, continuous function f on x, which takes values in 0 and 1 in the closed interval 0, 1, and the values on A will be 0 and the values on B will be 1, something like that. We proved that. Okay. Teacher's extension theorem is the following. If in case I have a, again, normal topological space and some closures of space of this, okay, um, then I can find and there is a continuous function f to r. Then this function, continuous function f, can be extended to a function on x to some other function f dash. That means f dash is continuous on x to r, and the f dash restriction to f equal to f. This is what I want to prove. Okay, which is not always, it doesn't always work out. For example, if I look at the interval 0 to 1, this is a subspace of 0 to 1. Now, this is not a closed interval. It's just a subset of 0 to 1. It's not in the usual topology, you know. Then if you look at the function fx equal to sine 1 by x on x in 0 to 1, I just avoided the 0, which is a problematic thing. And then this is a continuous function. It's continuous everywhere on 0 to 1. The trouble will be I cannot extend it to 0 to make it continuous, because the function's graph is, you know very well, it will be going like this, and then it starts oscillating infinitely often between -1 and 1. It oscillates infinitely often between the -1 and 1. So I don't know what is the limiting value I want to put. There is no meaningful limiting value for this function at equal to 0. So I cannot extend this function continuously to 0 to 1. Okay. Even though it's a normal space, this is not a closed subset. So if you have in a normal topological space a subspace F which is closed in X, if there is a continuous function from F to R, this continuous function has a continuous extension F dash from X to R. This is theorem. I want to prove this. We'll just prove this theorem, and that will be enough for today. Okay? Yeah? I have to prove metrization theorem beyond that. Anyway, we can do it some next time. Huh? So here is the theorem. Hmm? Let x be a. Oh, before the theorem, if you remember, what is Urjan's lemma really said to us? Urjan's lemma was this. I just want to repeat. X is normal space, and if I take a comma b are closed subsets of x, okay, then there exists a continuous function f from x to 0 to 1, continuous, such that f of a is singleton 0 and f of b is singleton 1. Okay? That's what I can really find. Of course, I can say 0 to 1. If we really look at it, I can make it closely a to b also. This function here, if I kind of find another function, maybe g, given by a plus b minus a into f, okay? What does this do? For any x, the value of fx is between 0 and 1, and therefore the value of b minus a into f is between 0 and b minus a. When you add, it will go up to b, okay? Right? So I can have this function. This function is from x to ab. And what is f of a? At every point in a, this function has the value 0, so this will be singleton a. And what is f of b? For every point x in b, f of x is 1. So if you put 1, a plus b minus a is b. So I can even write the theorem this way, that there exists a function g x2 ab. Okay, there exists a g x2 ab continuous such that the g of capital A is singleton A, g of, this is g of capital B is singleton B. Okay, is that right? So range doesn't have to be only 0, 1 as proven in the original. Range could be maybe goes into A to B also. And the values of the function on A is singleton A is A, and the values of the function on B are all B. Okay, I can assume that. I have proven this theorem. Region's theorem was proved. Now, teacher's extension theorem. It says the following: let X uh, be a normal space, and capital F be a closed space of X. Closed space of X. Right? Uh, if F is a continuous function from F to R, okay, then there exists a continuous function f dash uh, x to r such that f dash is restricted to f is smallest. So I have a continuous extension. This is what the theorem I want to prove is, okay, as this diagram shows. Okay, I want to prove this theorem. Here just extension. Actually, essentially, I'm doing all these things to actually later on prove metrization theorem under what circumstances the topological space um, is a metric space. That is, the topology comes from the metric of that space. Okay, that's what we want to prove. That is one particular metrization theorem is Urjan's metrization theorem. We'll do that in the uh, uh, next class anyway. Okay, so let's prove teacher's extension theorem. Hmm? Proof. Okay. Hmm? So there is already a small f from capital F to uh, let's say, go back. I said into R, right? No, not R. I will state it properly. Mm. Uh, I want it to be some kind of a closed interval. How about that? Okay. Instead of that, I want it to be closed interval AB. Take it back. Okay. Let uh, F be a continuous function from F to closed AB. Okay. Then there exists a continuous function F dash whole x to AB uh, such that its restriction to F is the small. Yeah, that's what I wanted to say. Not in general to R, to AB. Okay, okay. Let's prove this. I'll leave this here. Let's prove this. Hmm? The proof. Maybe A and B are both equal. If A and B are both equal, this is a constant function. And the extension is also the same constant. So there's nothing much to prove. Constant functions are continuous. Doesn't matter what topology you keep here. Okay? Uh, so that's it. So if A and B are equal, there's nothing to prove. It's obvious. But if A and B are different, then A is less than B, then you have genuinely a reasonable, a non-constant function, and etc. etc. So let's come to this one. Okay. If A equal to B, then F is a constant function. What is a constant function? Fx equal to A for all x in x. Then take f dash also from x to AB as f dash x equal to A. And then constant function is continuous, and so there's a continuous section. So let's assume A less than B. That means I want the function which has more values, not constant function. And let this AB be the range of the function also. Okay, so AB is the smallest closed interval which contains all the images of the function f. Let AB be the range of f. I just, f is taking values inside an interval, but it may not take some values. So I want to make that codomain as small as possible. So AB is the smallest interval which contains all the values of f. That's what I mean. Okay, that is AB is the smallest interval that contains fx. ff. F is only, small f is only a function and a capital F, right? I want to produce a function on the capital X. This is how we want to do. First of all, let us look at A naught. Okay, let's look at A naught to contain all the values of X. That means in F, hmm? Such that f of X is less than or equal to minus 1/3. You know what? I want to do the following. Assume A is -1 and B is 1. You can always do that. You can always do that by changing the small f into something else. Changing the small f instead of small f, you get a g to be divided with b minus a, and you can just make sure you compose with another function from ab to -1. You can have a continuous function which takes a to -1, b to 1. It's very simple, some linear function there, and then this f. And the composition of these two things is what phi circle f is from f to phi circle f is from f to -1 to 1. So I will operate with that phi circle f, not with f. So nothing wrong in assuming that you know a is -1 and b is 1. Now I'm going to look at A naught to contain all the elements of x for which fx is less than or equal to -1/3. And B naught is all the x in f such that f of x is greater than or equal to 1. This is actually nothing but f inverse of 1/3 to 1, which is a closed set. So inverse image is also a closed set. Similarly, this is f inverse of, excuse me, -1 to -1/3. This is a closed set in -1 to 1, and its inverse image since f is continuous is closed. So both A naught and B naught are disjoint closed sets. Hmm? then A naught and B naught are disjoint processes. Okay, and therefore you can produce a function. By the way, I'm going to call f naught equal to f. Okay, say these are disjoint processes. Then by Verson's lemma, there exists a function g naught, continuous function from capital X. These are disjoint processes in X. Actually, they are disjoint processes in F because these are only elements in F, right? But F is closed in X. I said the other day, if F is closed in X, every closed subset of F is also closed set of X. So these are actually closed sets in X also. Okay, first of all, closed sets in F, since F is closed in X, A naught comma B naught are closed in X2. So they are disjoint closed sets in X. Therefore, by Verson's lemma, there exists G naught X2. You know what? Minus 1 by 3 to 1 by 3. I can have any AB here. I have taken minus 1 by 3 to 1 by 3 continuous such that G naught of A naught takes the left hand minus 1 by 3 and G naught of B naught takes the right hand 1 by 3. Is that okay, sir?
Yes, sir.
Very good. Now I'm going to introduce put F1 equal to F naught minus G naught. Now the thing is, G naught is a function on capital X. F naught is a function on capital F only. It's only on the subspace. Okay? But this is on the whole space. So together, the difference is a function on the space capital F. Okay? This is a continuous function on capital F. Okay? This is capital F2. Where? Okay? I want to see that. Notice the following. F1 at any X, if I really look at it, if X happens to be in A naught, these values are all Fx is less than equal to minus 1 by 3. If I just want to explain. I'm just going to prove it to you that this is less than equal to 2/3. Okay? And yeah, I will prove to you that this is less than equal to 2/3. That's very easy. For all X in F, actually. X in F. Okay? So I take an element in F. That element in F can be in A naught or can be in naught and maybe outside A naught and B naught. A naught and B naught are two closed subsets of F. If it is in A naught, then the function values, if X is in A naught, then the function values are all less than or equal to minus 1/3 and greater than or equal to minus 1. And you are subtracting a G naught. And the G naught values between minus 1 and 3. So if I subtract some value between minus, actually on A naught, the value of G is not is completely minus 1 by 3. So you're subtracting minus 1 by 3. Minus 1 by 3 means you're going to add 1 by 3. F minus G naught is like you have to add 1 by 3 throughout. If you add 1 by 3, it is plus 1 by 3, it is minus 2 by 3, less than equal to 0. Okay? And if the element is in V naught, Fx is greater than or equal to, in V naught, Fx is, where is that? Fx is greater than or equal to 1 by 3 and less than or equal to 1. And but you are subtracting G naught. But the G naught and V naught is 1 by 3. So you are subtracting G naught means, right? is less than you are subtracting 1 by 3. If you subtract 1 by 3, it is 0 less than equal to f minus g naught. F minus g naught means f1 minus g naught is less than equal to 2/3. This is your f1. F1 is between 0 and 2 by 3. On a naught and b naught. But in between a naught and b naught, the g naught is always uh, in between a naught and b naught. The f is in case x is not in a naught in b naught, fx is between minus 1/3 and 1/3. Okay, Andy? And you are subtracting g also between minus 1 by 3 and 1 by 3. So if I subtract any quantity between minus 1 by 3 and 1 by 3, from the quantity from minus 1 by 3 to 1 by 3, that f minus g is definitely less than equal to 2 by 3 and greater than equal to minus 2. Is that okay, sir? And so that is why mod f1x is less than equal to 2 by 3. Okay? Of course,
Yes, sir.
mod, yes, please tell me. Very good. Hmm? Of course, G naught is in size less than equal to, and G naught x is less than equal to 1. Right? Okay. Right. I have created F1, uh, which is F naught minus G naught. Now, I'm going to once again look at two sets. These sets I'm going to look at is A1 to contain all the elements again of F such that F1x is less than equal to minus 1/3 into 2/3, and A1 is B1. B1 is set of all x in F such that F1x is greater than equal to 1/3 into 2/3. Okay, and again these are closed sets because F1 is continuous. So A1, B1 are disjoint closed sets in F and therefore in X2 and hence in X2. So there exists a function G1 continuous function on X2 by Urjan's lemma into I will take from minus 1 by 3 into 2/3 to minus 1 by 3 into 2/3 such that at A1 on A1 the value is minus 1/3 into 2/3 and on B1 this is the G1, right? Sorry, G1 and this is also G1 on B1 is 1/3 to 2/3. Okay, and then create F2 equal to F1 minus G1. Of course, F1 is F naught minus G naught minus G1. In other words, it's F naught minus G naught plus G. Okay. Once again, I'll show to you that this F2 x in modulus is less than equal to 2/3 square. Same argument I will apply on A1. On A1, F is greater than equal to, remember, minus 2/3. F1 is greater than equal to minus 2/3 and less than equal to minus 1/3 into 2/3. Okay, right? And there you are subtracting from that F1, you are subtracting G1. G1, which is going to take on this a value. So you are subtracting, that means you're adding 1/3 into 2/3. So when you add, this is the minimum value is 2/3 common into 2/3 common into minus 1 plus 1/3 is another 2/3 square with a minus sign. And on that side, F1 minus G1 is less than equal to, when you add this, it's going to be less than equal to 0. Okay, right? Right. When you added this, it's less than equal to 0. Similarly, you can prove that F2x is less than equal to 2/3 whole square. Okay. And already you said G1x anyway is less than equal to 1/3 into 2/3, right? 1/3 into 2/3. That was how you have done that. Hmm? So you continue this process and create similarly. Okay, create. So continuing, we get uh, uh, F1, F2, F3, and so on, and G1, G2, G3, and so on. All these functions are on continuous functions on X. All these functions are continuous functions on F. So continuous on F, and G1, G2, G3, etc. They come from the original lemma. Continuous on X. Okay, right? And corresponding sets An and Gn and so on, and mod Fnx is less than equal to 2/3 power n, and mod Gnx is less than equal to 1/3 into 2/3 power n, something like that. Okay. So I know actually Fn is F naught minus G naught plus G1 plus G2 plus etc. plus Gn. That's how we are always doing that. Okay. Actually, Fn is Fn minus 1 minus Gn minus 1. Sorry, it's up to Gn minus 1, I suppose. Okay. Okay. Now, if you really look at this summation, these are all functions on capital X. Okay. And mod Gnx is less than equal to 1/3 to 2/3 power n. And so you can apply Weierstrass a convergence test to show that this partial sums 3 actually converges uniformly. Because what is the sum of all of them? This is 1/3 and sigma 2/3 power n, and going from 0 to infinity is 1/3 by 1 minus 1/3 is less than equal to 1. Okay. So since sigma 1/3 into 2/3 power n equal to 0 to infinity is equal to 1, converges, right? This Sn equal to G naught plus G1 plus etc. plus Gn minus 1 converges uniformly on X to some function. Okay? To some function F. To some function F. Function. Maybe this is the F dash I want to take. Okay? To some function F. So coming back. So this that means this Fn's are functions on F only. This is converging to F dash. Okay. On also this is less than equal to 2/3 power n. So as n tends to infinity, Fn tends to 0 uniformly. Because Fn is 2/3 power n. So Fn tends to 0 uniformly. Therefore, that converges to this F naught on F. Yeah, beautiful. I think this is done. Right? So also, Fnx is less than or equal to 2/3 for n for all x in F implies Fn converges uniformly, converges uniformly to 0. Therefore, Sn, which is your G0 plus G1 plus G2, etc., plus Gn minus 1, okay, converges uniformly to F0. To F0. On F, see, there are two things going on, right? This is only on a capital F. They are on capital X. So they can be viewed as functions on capital F also. On capital F, okay, why? Because this is going to 0 and this is going to F dash. So this is going to 0. So F dash goes to F dash equal to F0. This converges to F dash and that F dash, but this converges to 0. So this converges to F0. Okay. I think the same thing I'm saying again and again. That's what it is. This converges to F0 and F. But that is F dash equal to F and F. We finish the problem. This is teacher's extension theorem. Okay. Nice. Hmm? Yeah. Then we have, very good. Hmm? Then we have Urajan's metrization theorem, or in Urajan's embedding theorem. Okay. Right. Basically, I want to embed it in a metric space. The metric space I will take is probably I, which is interval 0 to 1, with itself infinitely many times, I omega or I infinity. I would like to show you that if a topological space X is a normal and second countable, if both are there, then I will be able to get a homeomorphism from X into I infinity. And this will be a metric space. Okay. And so I can embed this into a metric space. Embed means I can get a homeomorphism onto some subset. Okay. Right. And so if you restrict yourself to that subset, X is homeomorphic to that subset, and there's a metric space. This is what I would like to. I'll state the result, and maybe we should not go too far off. Okay. So let's see that. Let X be normal and second countable. Normal and second countable. Then there exists a homeomorphism. Then there exists a homeomorphism uh, from X into X onto a, subspace, subspace of I power infinity. Okay, that is 0 to 1, infinitely many copies. Okay, this is what the embedding is. I can embed the topological space into that. And this is a metric space we'll usually show you there. And this is homeomorphic to a subspace or a metric space. So this is a metric space. This is what this theorem is all about. Okay. Well, that's again quite a long theorem. I can probably, yeah, finish it off. Okay. Maybe we'll just finish this theorem also. Not a problem. Okay. So let's say Urjan's uh, embedding theory. We finished the previous sections here very quickly, so no problem. Urjan's embedding theory. Okay, so let X be a second countable normal space. Let X be a second countable normal space. Okay, uh, then there exists a homeomorphism F. Homeomorphism means what? Uh, it's a bijective mapping, continuous, uh, and inverse is also continuous. Okay, there exists a homeomorphism F of X onto a subspace of X onto a uh, subspace of R infinity. Well, we do more of R infinity. Actually, I will essentially show -1 to 1 for infinity. Okay, of R infinity, and therefore X is metriable. That's the thing. Actually, I don't have to have all of R. -1 to 1 is what I will really ensure it happens. So it doesn't matter. Okay. So second countability and the normalcy together will ensure that the space is metriable. Mm, I think second countability is essential. Without the second countability, you don't get metrization. I will have to give you examples of normal topological spaces which are not metrizable. Second countability becomes must. Okay. Mm, okay. Let's see that. Proof. The space we have taken X can be only a finite space. Then there is not a big deal. If you have only finitely many points in that, they can always be mapped to finitely many points there. And a finite subset of R infinity, it's only a discrete topology. Because if you look at finite subsets in any metric space, uh, if you have only finitely many points, what is the topology? I have finitely many points inside a metric space XD, for example. Huh? What is the topology? Are these things? It's a discrete space only. Because topology is like take open sets in the original space, which is you are talking about R infinity, right? Which you take open sets containing these points. So, for example, here is an open set in R infinity whose intersection with X will contain only that point. So that point becomes that singleton element becomes open set. Every singleton becomes open set. So it's only a discrete topological space. So in case X is finite, there is nothing to prove. X is finite, then X is a discrete topological space. X is homeomorphic to a finite set. X is homeomorphic. X is, what is homeomorphic? It's obvious. Okay. Uh, I didn't tell you, if you have a finite space, suppose X has only elements X1, X2, etc., Xn, there is already a metric. You know the metric distance between any 2 points is 1 if X is not equal to Y, 0 if X equal to Y. Suppose you put that as a metric. Point, 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 point. This is by itself an open set, open set, open set, open set, open set. Because if the distance from here is less than half, then only 1 point is there in that, because the distance to any nearby point is 1 only. If you want distance to be less than half, if you take a ball of radius half centered at any X that contains X alone, so that becomes discrete space. So already there's a discrete metric space. That's a metric space. And if you put that many points in R infinity, that is also a discrete space. It inherits the topology from the metric space of R infinity, but that is also discrete. Both are homeomorphic. There is nothing to prove. In case X is finite, then right, um, then I already have a metric on it. This is a metric I can use. In case X is finite, then X is a metric space with metric D given by dxy equal to 1 if x not equal to y, 0 if x equal to y, and then xd is a discrete space, is a discrete topological space. Discrete space means every singleton is also open, is also closed, is discrete topological space. And a subset of R infinity, a discrete subset, a discrete, a finite subset, a finite subset of R infinity, having exactly as many elements as X has, having exactly as many elements as X has, inherits topology from R infinity, and that is discrete topology. Inherits topology from R infinity, and that topology is, and that inherited topology, and that inherited topology is discrete space, is a discrete space too. So X is homeomorphic to that space. X is homeomorphic to that discrete space. There's nothing much to talk about there. So I assume that X is infinite. And I'm looking at a countable base, So let X be infinite. Okay, and you have a countable base. Okay, second countable topological space, right? Let Gi I in some indexing set. Indexing set is actually countable, so it may be I equal to 1, 2, 3, 4 ad infinitum, right? And that's what it is. I may be taken as a natural number. B, a countable base for X. Okay, sir. Now, what I would like to do is, that's a basis. So if you take any element X, it is in some basic set Gi, but it is a normal topological space. Therefore, I proved that I can squeeze in an open set in between the two things. Okay, maybe some other Gj, such that Gj is X is in Gj is contained in Gj bar is contained in Gi. I can do that also because Gi complement is a closed set. Okay, so I can do that. Okay, and maybe I call this. Okay, so for each j, some natural number. Okay, there exists a Gi. There exists an I, also a natural number. So that Gi is contained in Gi bar is contained in Gj. How to create that? I just told you. You take a GJ, take any element in that. The non-empty open set. You take GJ in that. And because of the normalcy, the singleton X is closed and the GJ complement is closed. And so these two closed sets can be separated by two open sets. And I call this open set GI, and this called H. So X is in GI and GI is in H complement. That means GI bar is in H complement. Okay, and the H complement is contained in GJ because H is contained in GJ. H contains GJ complement. So H complement is contained in GJ. So all that I wanted, I just say if I have a GJ, there is a GI, so the GI is contained, GI bar is contained in GJ. And every time I have such a pair, I have this GI GJ. I have constructed this GI GJ. Okay, so consider also GI GJ. Consider all such GI GJ pairs, such ordered pairs. GI GJ. First of all, I is countable. I is any natural number. J is also a countable set. So, such ordered pairs. So, what do you mean by such ordered pairs? In this, J is contained, J bar is contained. That's how this order pairs are chosen. And these are countable many. These are countably many. So, call them. So, let them be. Let them be P1, P2, P3, etc. These are the pairs. First pairs, second pair. Pairs are countable. I can write. I can order them any way I like. I just ordered them. Just a minute. Okay. Excuse me. So I added them like that P1, P2, P3, etc. Good. Then for each pair, Pn, Pn is some pair, J, G, J. Okay. So how is that pair? There is a Gi contained in Gi bar is contained in Gj. That means Gi bar is a closed set and Gj complement is a closed set and their intersection is empty. So these by our original lemma, I can have a function which separates these two things. For each pair, there is just a function fn x2 0 to 1 continuous such that on gi f of gi is 0 and f of gj complement is 1. Okay, is that right? For each pair Pn, I have a function Fn. So I have infinitely many functions F1, F2, F3, etc. I'm really trying to look for a homeomorphism from X2, as I said, 0, 1 to the power of infinity. Okay. So each element in this should be mapped to infinitely a sequence in 0, 1. Right? What is this? This is nothing but 0, 1 cross 0, 1 cross 0, 1 ad infinitum. Okay, so an X will be taken to elements here. An X will go what? To infinite entries here like that. And so define F from X to I infinity, I being 0 to 1. I can actually take I to be R. It's not important for us. 0 to 1, okay, by, yeah, f of x is equal to, what is this? f1x, f2x by 2, f3x by 3, and so on, 1 by n, fn x, and so on forever. Okay, I think that's going to define a mapping. Okay, this defines a mapping. This defines a mapping f from x to 0, 1, infinity. Okay, I want to show it's continuous. Its inverse image is bijection, and its inverse image also is continuous. Bijection is not going to be very difficult. Okay, f is a bijection. First of all, what is this? This is actually, see, I put 1 by 2, 1 by 3, 1 by n for the following reason. If you really look at the norm of this, so mod f1x whole squared, 1 by 4, f2x whole squared, 1 by 9. So since sigma 1 by n squared, n equal to 1 to infinity converges, that is genuinely a point in 0, 1, infinity. Okay, it makes sense to talk about that, right? And this element f is in 0, 1, infinity. Okay, now f is 1, 1 is very easy. F is 1, 1 is very easy because for x comma y in x, x not equal to y, because of the Hausdorff property also, I can have different open sets around x and around y. Okay, there's x here, there's y, there's different open sets. It will be separated by different open sets. But then I can actually take a basic open set containing that and basic open set containing that. So I can have two disjoint basic open sets, GA and GJ, in which x is in this and y is in that. Okay, and therefore, as far as this is concerned, you see, if you look at this GA GJ pair is there. If this is PN, what is really FN doing? FN will send the elements of GI bar to 0 and the elements of GJ complement to 1. Now X is in GI, so it's FNX will be 0, but FNX will be 0. What about FNY? Yeah, I think FNY does not go to 1. Okay, okay. Yeah, no, I can do this. I can squeeze in between these two things another open set, and so that outside this, because GI is contained in some other, yeah, you can do that also. You don't have to use this. GJ is not a something surrounding here. GJ is somewhere here, so that GJ complement contains that point. Then FNGJ complement is 1. So you see that. So the nth entry for x is 0, for y is not 0. Because of that, I get the 1 oneness. So f is 1 1 is obvious. Okay, right? We choose GIJJ so that x is in GI, because the Hausdorff property should be used. Okay, and then you get that x is in GI is contained in GI bar is contained in GJ, and x is in GJ complement. Y is in GJ complement. I can do that. Then if GI GJ is some number, this is some Pn. Pn or Pn, then Fnx is 0 and Fny is not 0. So that's it. Nth entries don't match. Therefore, Fx is not Fy. So F is 1. Okay, so that means it's bijection onto some subspace of that. Okay, only I have to show it's continuous. We shall show now that both F and F inverse are continuous. We shall show that both F and F inverse are continuous. Let's talk about continuity of F. Okay, F is a function from x to 0, 1 power infinity, right? So continuous means, okay, for every epsilon greater than 0, there should be an open set here. Take an x naught in x. You have to show that for every epsilon greater than 0, there exists an open set G containing x naught such that f of x minus f of x naught is smaller than epsilon for all x in G. That's what your continuity means. Okay. So take an epsilon, let epsilon be greater than 0. And first of all, take an x naught in x, continuity of f. Let x naught be in x. We show f is continuous at x naught. So take any epsilon greater than 0. I have to produce an open set G around here. So take any epsilon greater than 0. Okay. Right. I have to get an open set so that an open set G such that for every x in G, fx minus fx naught norm of this is less than epsilon. So for any x, I will tell you the G later on. Okay, for any x in x, I don't want to take the whole of x. I want to take an appropriate G. I'll tell you how to take that. For any x in x, norm fx minus fx naught. The norm is what? This is the norm in IA infinity is sigma mod fn x minus fn x naught. Actually, the values there are 1 by n squared by n squared n equal to 1 to infinity. This is convergent. Okay. I want to make it very small. That's what I want to try to do it. Right? So this converges, only I want to make it very, very small. Because it converges, the tail end becomes as small as you want. Because of the presence of epsilon, I can say that this is less than equal to, I take bulk of the matter first, sigma n equal to 1 to some n naught mod fnx minus fnx naught by n squared plus the tail is small and that is smaller than some epsilon squared by 2. Okay, I can choose such an n naught. Okay, choose an n naught, a natural number, such that this happens. Okay, right. But the first n functions, they're all continuous functions, and therefore I can make the difference between fnx and fnx naught small, provided because each of these fn is a continuous function from here to 0, 1. Okay, and so for each 1 less than equal to some k less than equal to n naught. Hmm? This fk x201, remember, is continuous. So there exists an open set. There exists an open set gk, open set gk. Oh, I have already those. Yeah, I can find some open set gk such that x is in gk implies fnx minus, okay, fnx minus fnx not fn fk, mod fkx minus fkx naught. When it is in this, it is less than whatever you want, less than epsilon squared by, I will make it epsilon squared by some 2n naught. Okay, this doesn't matter. Epsilon squared by 2n naught. I can make it as small as I want. I made it smaller than epsilon. So I have finitely many open sets here. Okay, and their intersection is a, I think that's what I do that. Maybe I should not call them GK, call them some HK. Doesn't matter. Some open set. Now, intersection HK, K equal to 1 to n naught is H. This is open to, is open to. And what's happened if X is in H, then this difference mod Fn x minus Fn x naught, okay, Fn x naught is less than epsilon by 2n naught, sir, for all n equal to 1, 2, etc. n naught, because this H is contained in every one of them. So as such, therefore, when X is in H, what do you notice? That this norm, norm fx minus fn fx naught is less than or equal to, here, I have n of the objects, each is less than epsilon by 2 n naught, and n naught such objects, so n naught into epsilon by 2 n naught, plus another epsilon squared by 2 n 2. Okay. Oh, I have squares. Why did I forget the squares? I forgot the squares. Okay. So when I put the squares, n naught into epsilon squared by, epsilon squared by 4 n naught square. Doesn't matter. Okay. Epsilon squared by, I can make it small, right? Right, isn't it? So by n naught square is also there. Okay. Doesn't matter. Fnx minus, yeah. Yeah. I can make it. That's okay. Extra n naught square is there, right? That's not an issue. For each n is a fixed quantity, so I can suppose this by n squared. This by n squared is made smaller than 1 by epsilon. Yeah, that's good. That's better. Okay. So that's fine. So epsilon squared by 2 n naught. Plus, I think so. Plus another epsilon squared by 2 n naught. And this is epsilon squared by 2, that's epsilon squared by 2, plus epsilon squared by 2. So it's epsilon squared by epsilon squared. I can make it small. Okay, right? So what did I prove? I proved that f is continuous. That's it. Very nice proof. Okay, I was a little not. This is nothing. This fine. Okay. So first of all, having done that, each fn from n equal to 1 to n naught are continuous, and so they can be made very small by making sure appropriate open set is taken inside x. Whenever x is inside h, I can make it as small as I want. And for each fk, I have one hk, but their intersection is finite intersection only, so that is also open set. So when x is in h, x is in every one of them, and therefore every one of them is small, and extra the tail is anyway very small, so it's working out. Therefore, that's good. That's good. F is continuous. Finally, I have to show that F inverse is continuous, and that finishes the proof. Okay. Now we show F inverse is continuous. Oh, F inverse means you're going from this I infinity back to X. So this is what you want to show continuous. That means for every open set here, I should be able to get an epsilon greater than 0. So for every open set G, open in X, you want to find an epsilon greater than 0 such that, okay, whenever I take two quantities X and Y in I infinity, and the distance between X and Y is less than epsilon, then I have to show that maybe X is in G, and then I have to show that Y is in G too, something like that. Okay, I want to show F inverse is continuous at each point. So there is a point. That point will go to here. Maybe some X naught will go to Fx naught. That is here, and I want an open set of Fx naught in G. For that open set, I have to find an epsilon greater than 0. So let's start with that. Okay. So take any, here I am taking, okay, maybe I can take X naught here, doesn't matter. I infinity to X. Okay. Let X naught belong to, X. Okay. So we are supposed to produce an open set. Yeah. No? We must produce and no, sorry, no, for every open set, you have to produce an epsilon greater than 0. That's what it is. Okay. For every open set G, X naught in G, open set G in X with X naught in G, we need to produce an epsilon greater than 0 so that, okay, so that when I take elements in I infinity, okay, elements in I infinity are like images, right? So that Fy minus Fx naught is less than epsilon implies Y is in G. That's what we have to prove. Okay? Very good. So let's prove that. Okay? Very interesting. Okay? For each, you wanted to prove it for each G means maybe basic neighborhood is okay. That's good enough. So for each Gj of X naught. Okay? That's good. Then he uses Gj is there, right? So because Gj is there, we can find Gi so that the pair that means so that so that Gi is contained in Gi bar is contained in Gj, and you have this pair Gi Gj is there. It has its own name. Maybe that is Pn naught. And you is very nice. That is Pn naught. And he says choose epsilon to be 1 by 2 n naught. Okay. If you take epsilon to be 1 by 2 n naught, anything less than 1 by 2 n naught, then what happens if mod Fy minus Fx naught is less than or equal to less than epsilon, okay, would imply this is by definition sigma mod fny minus fn x naught by n whole square, right? This is going from n equal to 1 to infinity, and that is less than epsilon. Okay, that is less than epsilon, and I can take epsilon to be smaller than that, and therefore that is less than 1 by 2 n naught squared. Because this is actually square of this. Okay, because I didn't take square root. Is less than 1 by 2 n naught square, and that means every term is also less than that. In particular, the nth term is actually less than that. Therefore, f n naught y minus f n naught x naught by n squared, right? N naught squared whole squared is less than 1 by 2 n naught whole squared. N naught squared, if I cancel, then I get that fn y minus fn naught x naught in modulus is less than 1 by 2, right? After canceling the n naught squared, I have 1 by 2 whole squared. So if I take square root, fn naught y minus fn naught x is less than 1 by 2, okay? So therefore, mod fn naught y minus fn naught x naught is less than 1 by 2. I think we'll be done with that somehow or other. But what was fn naught? You remember pn naught is your GA, okay? So what does fn naught does? Fn naught sends every element in GI to 0 and every element in GJ complement to 1. That's what fn naught does. Okay, so x naught is in GI, so this is 0. Okay, and therefore fn naught, right? Fn naught x naught is 0, and fn naught y in modulus is less than half. So that is not in GJ complement. That has to be in GJ. So mod fn naught y is less than half. Therefore, y is in GJ. Because y cannot be in GJ complement. It has to go to 1. It has gone only to a quantity less than that. So y is in GJ. Isn't that what I was trying to tell you? I was trying to tell you. That's what we were promising. Okay. Did I erase that part there? I erased that part. Okay. No problem. That was what I was promising. In order to show that the function f inverse is continuous from I infinity to f of x. In order to show that, take any point here, there is a point coming from here, x naught. Then for every open set around x naught, I should be able to find an epsilon greater than 0, such that whenever fy and fx naught are within that small epsilon distance, then fy is in this open set, or y is in the open, y is in that open set. And that's what I managed here. Yeah. So this fields f inverse is also continuous. So that is how, I mean, let us look at the essence of what we have done. Essence of what we have done is, sorry, is the following. That, yeah, we have to go back. So essence of that, ooh, and we did quite a bit. The essence of this is this, that any second countable normal space, it is homeomorphic to a subspace of I infinity, actually R infinity, doesn't matter. And the metric structure here will be uh, uh, imbued or will be inherited by this the homeomorphic copy. And so therefore X itself is a matrix. So that's what it is. And we will show later on that I have to give you some examples where if I don't have second probability, would I just still get this embedding or not? We don't get. That's it, sir. I mean, I thought of proving this next time, but I proved this also. Okay, and that's enough for the.
Yes, sir.
Sir, any questions or comments? All right, sir. So,
Fine, sir. Thank you, sir.
yeah, that's
Uh,
nice. And, uh,
uh,
we are
sir,
doing very
we,
well. We have finished the separation actions too mostly.
okay. Sir, we were having just before the class, we were having a chat, Yashodhar Garu and myself.
Mm-hmm.
Maybe you want to talk to him once.
He wants to talk to me?
No. Maybe you want to talk to him once.
Yeah, I'll do it. Yeah, one second. I can. Yeah, no problem. Okay. He will look at this lecture. He will follow it. If there is a necessary, I'll talk to him again. Um, so, yeah, we have done very well. We have just
Yeah.
uh, uh, we have connectedness to talk about next. Maybe I say a few more examples and then go on to connectedness. We are doing well. Maybe in about a month time, we may be able to finish this course. Less than that much, maybe we can finish. We'll be able to finish the course. Okay. All right, sir. That's it.
Thank you, sir.
Okay.